Hello everybody, my name is Yoonhyuk Ra and I am currently a postdoctoral researcher at Professor Kyoungsik Yu's lab here at KAIST Electrical Engineering. Today I am here to introduce our recently published paper titled Low Power Coherent Ising Machine based on Mechanical Kerr Nonlinearity. Now, before we start diving into the details, let's briefly go over the basic concepts starting on what an Ising machine is. As we can guess from the name, the term Ising machine comes from the Ising model, which is a well-known model in ferromagnetics used to study the behavior of spins. So let's imagine two magnets that interact with each other, and in this case, in opposite directions. If we align the two magnets in a random formation and let go of them, they will evolve until one magnet has spin up and the other has spin down. This is due to their interaction, which can be seen in this case as an anti-ferromagnetic interaction. Now, if we look at in the view of the entire system, the anti-aligned status shows a lower energy configuration. So the spins align themselves depending on the type of interactions, but we can also see them as a system trying to reach the lowest energy status, which nature prefers because a higher energy system is usually more unstable. Now, two magnets seem quite simple, but things can get complex when the number of magnets increase and also the connections become complex. This system of magnetic spins interacting with each other forms an Ising model, and the Ising machine is a type of hardware solver that solves the Ising model, or in other words, uses a certain set of steps to find the lowest energy configuration. Now let's imagine the situation where there are n spins. Each spin can either have a spin up or down state, which means that the total number of configurations is 2 to the power of n. So even for just 100 spins, we have over 1,000 billion possibilities, and that is a 1 with 30 zeros behind it. The sheer number of cases makes conventional computers extremely hard to solve these type of problems. This is where quantum computing can really speed things up and easily beat classical deterministic Turing machines. In a conventional digital computer, a certain state can be represented as a sequence of ones and zeros, which are basically normal digital bits. We randomly select a digit, change its value, calculate the energy, and compare it with the previous status. If the energy is lower, we accept it. If not, we go back and randomly select another bit. This is a form of so-called simulated or thermal annealing, which is a straightforward procedure of exploring the energy landscape in order to reach the ground state. But we can easily imagine the situation where the status is stuck in a local minima, which is of course not the optimal state. To prevent this situation, we accept a higher energy status with a low probability to overcome these stuck situations, or to say jump the energy barrier. However, this still takes a lot of time and isn't the ultimate solution. The main reason why we cannot easily overcome this local minima trapping is mostly because modern computers can only represent one state at a time. A 0 bit is an absolute 0, and there is no any form of any information related to a 1 value. Now, for people familiar with quantum computing, we can guess at this point the power of superposition, where a 0 and a 1 is both encoded into a physical element, which we mostly call qubits. And we also know that optics is a great platform for superposition. So if we go back to the energy landscape, imagine that the evolving system contains every possible configuration with each a small probability. So every type of configuration is superpositioned. Now, evolving the system will automatically make the spins aligned into a lower energy status, not due to some algorithm, but because it is the law of nature itself. So the process itself is simple and straightforward, but the hard part is simulating the spin itself. We need a certain physical element that not only mimics the properties of physical magnetic spins, but we also need to be able to easily control them. So in recent years, there has been vast research on finding a way to implement these magnetic spins into physical bodies that we can access easily. We have seen Ising machines made of pulsed light in optical fibers, spatial light modulators, electronic circuits, integrated optics, and hybrid electro-optical platforms. We can see that each method possesses a unique and interesting way to solve the Ising model. But just like electronic circuits, humans in the end will always look for an integrated platform, which is essential for mobility and also stability. This is where our research starts for looking for an integrated optical Ising machine, and when it comes to on-chip platforms, power becomes a critical factor. Actually, there has been reports of integrated optical machines, but one factor depicts a problem towards large-scale integration, and that is the power. So previous reports use ring resonators to harness a certain nonlinear effect called the Kerr effect, where the refractive index is affected by the optical signal passing through the media. This is why ring resonators are used, because they can build up a large amount of power rather than waveguide structures that just make the light pass through. The problem is, the Kerr effect is a very weak phenomenon, even in ring resonators, which is why we need a large power to harness the effect. If we say that we have a successful spin model using the Kerr effect, and it takes 1 milliwatts of optical power for one functional spin, we need 100 milliwatts for 100 spins. Now, considering the power of moderate lasers mostly used and the damage threshold of optical components, higher powers can easily become inappropriate. Improving the quality of the integrated components can lower the power threshold, but we mostly have a certain limit for quality improvement, and they mostly do not provide us the ultimate solution. However, ring resonators are still appealing, not because they can help enlarge the Kerr effect, but because the optical response easily shows a nonlinear behavior. To represent a binary state operation, or in other words, to represent the up and down spin, we used a set of two resonators. We got this idea from a previous report where a set of resonators were used with a feedback loop for interaction between the resonators. We did actually make the chip and demonstrated the model itself, but as said before, power turns out to be the main problem. So what we need is a form of interaction between the resonators that kind of pushes one resonator and pulls the other in a certain physical matter, or in other words, some kind of directly opposing interference between them. Since the power inside a ring resonator is dependent on the detuning between the resonator resonance and the optical pump frequency, finding a mechanism that can shift the resonance in opposite directions will satisfy what we need. This is where our work comes in, where we implemented a MEMS-like structure between the resonators that is driven by the optical gradient force, which is a type of mechanical force that originates from strong evanescent fields between dielectric media. The system starts with the actuator in the middle, so the effective index of the sections in both the resonators are identical. A small optical power imbalance between the resonators will generate a non-zero net gradient force and pull the actuator towards the resonator with a larger power, which will affect both the resonators' resonance wavelength. The resonator with the actuator, which moves towards 2, will feel an effective index increase due to the decreased gap, and at the same moment, the other resonator will feel an effective index decrease. This will redshift one resonator and simultaneously blueshift the other, changing the optical power inside the resonator due to the detuning shift. This shift in both resonator resonances will further on increase the power imbalance until the net optical gradient force is balanced by the spring displacement force and reaches steady state. This direct interference between the resonators enabled by the actuator greatly reduces the power threshold because it brings direct opposing interference between the resonators. Even if the mechanical Kerr effect was small, let's say on a similar scale to the optical Kerr effect, the unique interference mechanism still will greatly lower the power threshold. The final state collapses into a binary state operation where the final state is determined by the phase relationship between the pump and input signal. So, to sum it up, the power threshold is greatly lowered not only by the larger mechanical Kerr effect, but also by the unique interference mechanism, which was unforeseen in similar resonator-based systems. So up to now, that was the first major aspect of our paper where we went through the origin of such the low power operation. The coupling interaction between the spins is performed by coupling a portion of the output signal into the input port of coupled spins, which is a common method used in optical Ising machines. Now, since this part is not a major part in our paper, we will leave the audience to look it up in similar reports. Now, the second major aspect of our paper, although not mentioned in the title, depicts a very special annealing method which we named the point annealing method in our paper. So once we operate the spins, they will fluctuate until they reach a certain status and become fixed. In the early stages, the fluctuations are large, but once they pass a certain point, the status somewhat becomes irreversible. So if we think of the spins as a certain particle-like formation, the evolution of the spin system kind of resembles a high-temperature liquid cooling down and reaching a solid status. So let's imagine a small body of molten material cooling down to below the freezing point. If the body is cooled simultaneously, then small crystals will form randomly and start to grow. The crystals will grow larger depending on the cooling speed and will eventually meet, but different crystals probably won't be combined into a single crystal because at the boundaries where they finally meet, the alignment of, let's say, the molecules won't always agree with each other, eventually leading to a polycrystal formation. The boundaries are called domain walls or also grain boundaries. Now, let's say we can select a very small region of the material and start the cooling process from that point. For example, we can take a cooling needle and stick it at a certain point of the material. At the point where the cooling starts, a small crystal will first form and start to grow as the cooling further takes place. Rather than cooling the entire body, the cooling gradually is spread to the system starting from the selected point. And if the cooling speed is carefully controlled, we could end up in a situation where the small seed crystal has grown to the entire system, leading to a single crystal formation without domain walls. So now we have a single crystal, which is obviously a lower energy state than a polycrystalline structure. This can also be applied to the Ising machine. If we start the operation of a single spin before initiating the other spins, the fast relaxation will act like the single seed crystal, and the spin evolutions will slowly spread throughout the entire system. The evolution speed is slower, but we can get a higher chance of reaching a lower energy state since domain walls can be avoided. So we start with both a spin array of 625 spins in a square lattice where each spin has a ferromagnetic interaction with its neighboring spins. Blue is spin up and red is spin down, so the ground energy state is all spins blue or either all spins red in the end. Now, both starting from a random configuration driven by noise, the left image shows the spins evolving when simultaneously cooled. As we can see, domain walls start to appear, and after a certain point, the energy of the system becomes constant and stops dropping. Now, the right side of the picture shows what happens when we start the operation at a selected point. Since noise is always there, all these spins do fluctuate in the initial stages, and as the so-called cooling proceeds, we can see a single domain gradually growing into a large domain. This will eventually prevent the formation of multiple domain walls, and as we can see in the energy graph, it reaches a lower energy state, which in the terms of an icing machine has reached a better solution. This is the point annealing method introduced in the latter part of our paper, where we named it from the aspect where we select a single point and start the annealing process from that point. The mechanism itself is quite simple and straightforward, but actually implementing it into an icing machine is a different problem since we need to be able to have individual spin control. Luckily, this can be easily done with our model since the individual photonic circuit in our integrated platform can be accessed easily. All we need is a stronger input signal in the selected spin, while the input signals to other spins are set to 0, with only the pump signal on. And of course, our calculations have shown good results of obtaining a better solution in arbitrary graphs, which is why we would like to say our model can show significant impact when realized together with this method. So that's pretty much the two important aspects of our paper. And before we move on, I would just like to go over a few points about the icing machine. So first, the icing machine can be seen as a special type of quantum computer that can solve discrete optimization problems. The main difference between a possible universal quantum computer is that it does not perform calculations using certain operation gates, so we probably can't use it for every application. However, since it is a special type of solver based on a natural phenomenon, it serves as a very quick problem solver to specific applications, but the good thing is that actually many daily life applications can be modified into these combinatorial optimization problems, such as the traveling salesman problem, drug discovery, protein folding, and etc. And since it is also a direct simulation of a spin system, we can also think it can function as a quantum simulator itself, which can always give us a better understanding of nature. Now let's check out how experiments are done in our lab.